we use a method here in Nottingham, which is called Dynamical Energy Analysis, and I'm going to use the next 50 or 60 minutes to give you an overview of that method. It was developed here around 10 years ago and then steadily improved over the years, and I'm going to address that in the following slides. So I'm working here with Gregor Tanner, as well as David Chappell from Nottingham Trent University. And the kinds of problems we usually look at are this industry related problems of vibrational acoustics. So on the right hand side here, this is a model from which was given to us from FFT Belgium, now Hexagon. We are going to cover this model in more detail later on, but you can see that this is the result of a typical FEM calculation. So there was an excitation put somewhere around here. So this is a part of a car. Here would be the engine, then here would be the wheels here and over here, and then the passenger compartment would be here. And then there was an excitation put here, and then for a certain frequency, a numerical package was used in order to describe or calculate the vibrational response of the overall structure. And what would you do in order to do things like that? Well, normally the first step is to think of how to describe your problem. And all these methods, these FEM methods, they are based on the fact that you use a discretized mesh of whatever it is you want to describe. So if we would zoom in here, we would see hundreds and thousands and tens of thousands of triangles and quadrilaterals, discretizing this complicated structure in locally flat small patches. And then your aim is to solve some partial differential equations. So for example, here, the Helmholtz equation on this whole complex and complicated domain. And your discretization into this mesh allows you to describe, for example, displacements at vertices of this mesh cells by means of some discretization. And you could, for example, take this differential operator here and write it down in a finite difference form by assuming that the width of all the mesh cells is very small, so that this is actually justified, and then you go on and solve your equation numerically like this. Or alternatively, you use the same mesh, but then use test functions and rewrite your partial differential equation in a weak form, and the solution is then such that it is correct for a certain set of test functions, which would lead you to finite element methods. They all have in common that they describe these displacements, as I said, not in the whole space, but only on vertices here. So as indicated by these colorful arrows, you might have a little bit of excitation here and then a large amount of vibration going on around here. But in the end, this is just a discretized version of something which we all assume to be continuous in reality. And your discretization, as shown by these vertices of this toy mesh here, is only good as long as the resolution this mesh provides is somewhat comparable with the wavelength of any excitation which goes through this mesh. So as soon as you increase, for example, the frequency of an outer excitation, the wavelength will become shorter, and at some point your mesh won't be fine enough anymore to resolve all these ups and downs which travel through the continuous material in the background. So you will then have to refine your mesh, and this is exactly this increase of numbers of degrees of freedom with frequency Jonathan just mentioned. This can go up to a point where it's actually impossible to make this mesh any finer because it would just take too much time and effort to do so. There are ways around that, and we heard about a few of them yesterday in Alain's talk, and the most famous one is probably the statistical energy analysis. So the idea here is that you take this whole domain and you regard it as ergodic, as Alain told us yesterday, which means that, or simply put, you assume that the energy inside this whole domain is somewhat distributed equally throughout the whole domain, and you can therefore replace the whole domain by one number, namely the average energy in this domain. And then you can split the more complicated object you want to describe, say for example the part of the car, into weakly coupled subparts. All of them then contribute with their certain amount of average energy, and then you have to find out the strength of the coupling between these separate parts. And Alain mentioned yesterday that it's basically down to the difference of the modal energy in all these domains. So you can do all this, and this works very well for very high frequencies, but comes with two drawbacks. One is that you have to somehow decide which parts of your structure are ergodic and weakly coupled to each other. This can be a non-trivial, non-straightforward task to do, and in industry models, companies often rely on the knowledge of their engineers to be able to come up with such models. And the second drawback is that due to the fact that you simplify your view by reducing all of the complexity of this subpart here to just a single number, namely the energy content of it, you lose a lot of detail your model had to begin with. So in the end, you will be facing a result which only tells you there's much energy here and only a little energy on the other side of the structure, but the answer itself does not yield much detail. And these two things are things we want to address with this method of dynamical energy analysis. And how this comes about, I would like to tell you in the next couple of slides. So first of all, we mainly focus on Kirchhoff law thin shell theory. That means we focus on three equations in order to model the vibrational excitation of a mechanical structure. There's one for pressure waves, and it's a Helmholtz equation here indexed with a green P for pressure. And there's a shear wave of the same equation. The only difference is that the material parameters of the object, say the Young's modulus and the Poisson ratio and the density and the thickness of the plate, they all enter differently into these two quantities, Kp and Ks. And there's a third equation for bending wave or out of plane excitations, and this is governed by this biharmonic equation shown here. Now, as a mathematician, you would love to solve them analytically, but it turns out that for very complicated, or not even that complicated, but very fast, it's impossible to do so. So you have to resort to some numerical or approximate approaches. And one approximate approach is the one which then later on leads to ray dynamics, and that is by making an ansatz of a wave. That is, there's an amplitude function and a phase factor here with two unknowns. So we have this amplitude function and this phase function. And if you put this in, you're led to an expansion in terms of 1 over the external driving frequency, denoted with omega here. And if you discard terms which are very small due to dividing them by this very large number, then you are led to the so-called Eikonal equation. And while this equation looks considerably more horrible than the one on the left-hand side, it is simpler because it's just a first-order partial differential equation. And first-order partial differential equations have the big advantage that they can be solved almost in general, at least from a theoretical point of view, by using what is called the method of characteristics. So the geometry of the differential equations has certain simplicities to it, which allow for a common approach to solve them. And these characteristics then basically yield these things we already encountered in Jonathan's talk as rays. So this leads then to ray equations to approximate the wave intensity distribution instead of solving these equations exactly. So we have three types of waves: pressure waves, shear waves, and bending waves. So we will find three types of rays whizzing through all our domains. There will be rays for pressure, rays for shear, and rays for bending waves. They all have different dispersion relations. The first ones have the same functional dependency on omega, but different prefactors due to their different dependence on material properties. The bending wave equations the bending wave equation has a slightly different dependency on the external frequency. And just to give you a feeling of how this connection works from wave equations to ray equations, here's a tiny introductory example. Let's assume we have a plate. We are looking at this plate from the top. The plate has this color of dark violet, and there's a wall, a reflecting wall on the left-hand side. And let's assume we somehow manage to excite a vibration here in this Gaussian kind of shape, and let's also assume we manage to give it like an initial momentum so that there's a localized part of vibrational energy moving towards this wall, and I'm stepping forward in time here. As we can see, if we do this time evolution, this initial hump of vibrational energy does indeed follow a straight line, just as we would assume a classical ray would do. But if all I'm saying is true, then we would also assume that it would somehow interact with this wall and then be reflected in a specular manner. So let's continue our numerical toy simulation here, and we see interference fringes the closer we get to the wall, and then indeed, as soon as we continue, this wave packet, if you wish, follows this straight ray again. So this small, tiny numerical experiment hopefully convince you that this is a valid approximation, at least as long as the external driving frequency is very high. So classical rays it is what we are using for the energy transport. Now, where does this put us with respect to statistical energy analysis and finite element methods? So this is a plot we now have seen a few times already, yesterday from Alain, today from Jonathan. So there's a frequency axis, and for small frequencies, there are, for example, finite element methods you can use in order to describe your problem. Then for higher frequencies, and if you're fine with not getting a very detailed answer, but only an answer in terms of large excitations on the left and small excitations on the right, for example, then SEA would be one way to go. However, if you want to have more detailed answers, then we propose this dynamical energy analysis method, which would address the high frequency domain, but yield more complexity and more detail in its answer. There is again this mid-frequency gap Jonathan was talking about. So because we are neglecting all phase information, there won't be any effects which are grounded in diffraction or resonant behavior in DEA. Okay, having said all this, we are now facing the problem how to actually apply ray equations and ray transport in complicated domains, as for example this car body I showed you earlier. So how can we propagate rays through complex domains? And at this point I have to start a somewhat long detour, and I would like to be a bit patient and follow me throughout the next couple of slides. So first of all, we need to introduce something which is called the boundary map. And as Jonathan said, I will be talking about that in my presentation. I have no idea how he could foresee that. I come to think that this out of time license plate does mean he might have an actual working DeLorean in his garage. So let's assume we have an array emerging from this triangular domain. So imagine this is like a billiard table with hard walls at which a ray would be specular reflected. And then we can put an initial condition somewhere here, so that where this red dot is, and we could give it an initial velocity, if you wish, towards this direction. Now, one way of describing rays like this would be just to follow it, then have a reflection here, go over here, have another reflection, and so on, and always describe the position of the ray in terms of x, y, and then vx and vy, the two components of the actual momentum of the ray. And then they all would be indexed by time, and we could follow this ray in time throughout this domain. However, there's a more practical way of describing this ray, and this is in terms of boundary maps. And on the right-hand side, you can already see a coordinate system. So there's a coordinate called S, which ranges from 0 to L. Now, what is L? L is the total length of the exterior boundary here. So we start at the top and then go all this way around here. And this parameter S allows us to describe the position of this point here in terms of length along the boundary. So this is exactly like Jonathan said. This is one of the two parameters. I think he called it slightly differently. I'll call it S for the time being. Now, instead of looking at this point and this arrow, we can take this S coordinate, and at this S coordinate, we introduce a second parameter we call P, and P is the projection of this direction vector here onto the local boundary. So this projection here would be this short arrow in blue. It has a length P, and we can use this number P to do this, to draw this dot, this red dot here. And this red dot now corresponds exactly to this point here and this direction. And this is unique. As soon as I draw a point somewhere in this domain here, you know exactly where you are on the boundary and which direction your ray would emerge from the boundary. If the energy, or if the maximum velocity of the ray is known. Okay, so now we can go back to the left-hand side and propagate this ray forward in time. So there would be the next intersection here. So let's check that, indeed. And this yields another value of S. This is now larger because it's further away from this arbitrarily chosen 0 point here. And we get a new value of P as well, because after our specular reflection, the ray is a bit more tangential to this edge here. So this amount of P is larger, if you wish. And on the right-hand side, we can again draw a dot in our SP coordinate system. And this part of the ray here, connecting this point here and this point here, is actually a mapping, a connection from moving this point over to this point. Now we can continue to the next iteration. This time we end up with a smaller value of S, because again, this origin is here. So only this amount of S we have for this connection here, and then the next point would be here. So instead of following this ray here throughout this spatial domain, we can follow the whole iteration on this plot on the right-hand side. And this plot is called a boundary map, because this is exactly what it does. It maps the boundary onto itself, or if you think of trajectories, it maps trajectories from one boundary intersection to the next. I want to denote this with calligraphic M. It depends on two parameters, S and P, and maps them to the next version, S and P. This map M has two components. Let's call them MX and MY for the time being. This will be important later. Now, this is all fine and well, but for sure you will agree with me that the triangle is no car by no stretch of the imagination. So at least we have to get somewhat nearer or closer to actual FEM meshes. So the next step to take is that we have to focus on what happens if we glue several mesh cells together. Well, the first part is no problem. We can just, as before, denote a value of S and a value of P to this ray emerging here. And in this corresponding SP boundary plot, this would be over here. And just like before, we could follow this trajectory here, but at some point we are going to intersect the interface between the two mesh cells here. And at that point, we have to again go back to our boundary map and find out what are the S and P values for this point here. And it turns out you have to be consistent. So we first count the first triangle in total. These are these three patches here on this S-axis. So these dotted lines correspond to the vertices of the mesh. And then we take again another arbitrary origin. So for example here, and start counting in the second triangle from here on, so that we can attribute this value of S. So this plus this plus this plus this and then plus this to be the new value of S for the next iteration. And then once we have that, we can use the local tangent vector here. It points in the orange direction, and again project the current velocity onto this boundary to give us a projected velocity p, which now is negative because it points in the opposite direction compared to the direction of growth of s. Well, and from there on, we can go to the next intersection and repeat that and so on and so forth. So as you can see, this boundary map can easily be taken over to many domains. We could write down a boundary map like that for a much bigger mesh without any problem. It doesn't make much sense looking at the boundary map itself because it would be very complicated for a large mesh. But keep in mind, this boundary map is the one thing we will be talking about in the next slides. Okay. What I want to do now is I want to give you an example where we can actually fill out mx and my explicitly. And one example where we can do that is a circle. So now, instead of triangles, for a moment, I want to talk about circular domains. Please take my promise, we will get back to the car eventually. The circle has the big advantage that if we write down the dynamics in terms of a polar angle, phi, and an angle psi, which measures the direction with respect to the normal, then we can write down this boundary map, calligraphic M, explicitly. Namely, if we start at phi and psi, the next iterate will be at phi prime and psi prime, where psi prime is just the same value as psi, and the value of phi prime is phi plus pi minus 2 psi. This is not exactly the same as the boundary map I've shown you before in S and P, but phi is only scaled up to a value of 2 pi times the radius of r, so they are just proportional to each other, and psi and p would be linked by just the sign. So the sign of psi is plus or minus p. So having said that, we have to go back to our boundary map. So here it is. This is how the boundary map would look like for the circular billiard. So for example, if you would start here, the next iteration would be here, the next iteration would be here, then there's one here, then there's one hardly visible at the angle 0, and then the next iteration would be here again. So this is actually what is called a periodic orbit. So this orbit closes onto itself. If we started initial condition here, it would eventually fill out the whole horizontal line, and so you find a lot of behaviors. All initial conditions below 0 would go counterclockwise. No, they would probably go clockwise, and the positive ones would go counterclockwise. But it depends a bit on how you choose your system of reference. Okay, so we introduced boundary maps, and as I said, dynamical energy analysis is in the end rooted on ray dynamics. And all I've talked about so far is ray dynamics in very simple domains, but it's still simple rays. Now, dynamical energy analysis does things a bit differently from here on, namely that it focuses not on single rays, but on densities of rays. And the reason for that is twofold, and I'll address this later. But what does it actually mean to talk of densities of rays? This means that we are not just using single trajectories, but we can use a function, for example, a top hat function, which is 0 somewhere and then jumps to 1 and then jumps to 0 again somewhere else. And we can take a direct product in phi and psi direction so that we have a rectangle of initial conditions here. Now, this rectangle here is very small, so it means that the phi range covered is only very small, but it does mean that we actually start infinitely many trajectories for this tiny range of phi values here. And giving it an extent in psi direction means that there's not just one direction of rays emanating from here, there's a whole spread of directions. So this is the next important thing. We had the boundary map, and now we are talking about densities of rays. The next thing to explain is that we are not going to only map forward rays throughout this domain, but we are going to map forward whole densities of rays. Now, for the time being, please believe me that there will be an operator which does that for us. But for the time being, just let's assume someone gave it to us. Let's assume we can map densities forward through the domain. What would that mean? Well, the whole density here gives rise to a spatial representation like that. Again, keep in mind, what really happens is that we calculate this map on the right-hand side here using this equation here. The upper left-hand side is just the post-processing visualization of what is shown on the lower right-hand side. And mapping all these forward would mean that we reflect all these infinitely many rays here, and then they would bounce back off the wall down here, giving rise to a new densities of rays, now being a small patch here. So for the time being, we call this operator T, the transfer operator, and we will get back to it shortly. What does it do? It takes one density and maps it forward throughout the whole domain. And if we stick with our example of a small rectangle patch here, and we can actually sum up several contributions. So this is now the first contribution from our initial density, and this is the next iterate. We can add a third one and a fourth one, and actually infinitely many. So if we end up with an infinite sum like this would only work if it does converge, and it turns out it only converges if we introduce a small damping factor, for example, on each reflection. So now assume we have a continuous flow of particles entering the billiard here, but there's a tiny amount of absorption on each reflection, like it's, for example, the case in acoustic and room acoustics. So then you would constantly pump in energy, and without this absorption, you would pump in infinitely many energy, and the whole system would blow up in the infinite time limit. So due to this absorption, we'll get a steady state, and the steady state is called rho infinity. There's also a representation, of course, on our boundary map, and the density could look like that. Okay, we could also calculate more from this boundary density. Once we have that, again, I cannot repeat it often enough, this is the actual thing we have in hand. This is the thing we use to compute things. All the things we show on the top left here is just post-processing. And another form of post-processing would be to calculate the flow of energy. So you can actually use this and then calculate the directional flow of energy through a domain like this. We could also use other initial densities, for example, a bit broader, position somewhere else. So here you can see that instead of top hats, you could use a smoother function. This then has mathematically more interesting features, and it would converge better, and so on and so forth. But this is an aspect of the work I'm not going to talk about today. And you could again calculate the spatial representation. Again, the left-hand side is just the post-processing step of what is shown on the right-hand side. You could even make this more smooth if you wish. The value here goes smoother into a white value here to indicate this nice smooth decay, and you would be left with an initial density like that. Okay, so far so good. We have spoken about ray dynamics, we have spoken about boundary maps, we have spoken about densities, and I promised you that there will be an operator mapping densities forward through complex domains. And this is what we are going to talk about now. Again, we are staying with the circle. The reason for that is that for the circle, all these equations can be solved in a nice and compact way. So what is it we have to do? Well, we have this equation here for single rays, and now we want to have this operator T, which maps densities forward throughout the domain. Well, what does this mean? This means we start with a density, and it gives us a certain weight at a specific point of phi and psi, but we want to know what is the value of, or what is the weight after one iteration at a specific position phi prime and psi prime. And it turns out you can rewrite, or you can write the action of this operator in terms of this equation. This is called the Frobeniosperon equation, and therefore this operator is often called the Frobeniosperon transfer operator. And what does it say? It says the amount of weight after one iteration at this point comes from, well, go over all possible initial conditions, but only take those into account whose classical map gets you directly to the point phi prime and psi prime you're interested in on the left-hand side, and don't just take them into account arbitrarily, weight them with the amount of density which was at that initial condition. So this is how you have to read this lengthy expression. Now, if you want to do numerics, this is of not much use because it's a functional equation and the corresponding functional spaces are infinite dimensional. So you usually introduce some sort of basis set. And at this point, I want to introduce a Fourier basis. So instead of using a functional dependency on phi and psi, we introduce Fourier coefficients of this term on the left-hand side. So this is the Fourier coefficient Nm. That means that we have to introduce these two basis functions here and integrate over phi prime and psi prime, but there were two delta functions, so they drop out, and this is what we are left with. Then we can actually take our billiard map at hand and put that here. Oh, sorry. First of all, of course, we have to replace the Fourier, or we have to replace this functional dependency here with a Fourier sum as well. Now we are left with a sum over Fourier modes here. These are the coefficients, and we had to include the corresponding basis functions here. And now we can input our boundary map. So this yields this expression. We can reorder the terms a bit. So there's a phi dependency here and a psi dependency here. And you clearly see these just collapse to Kronecker delta functions. And this would collapse to a -1 to the power of n. Very good. So this is our final example for the transfer operator for this very simple circular case. Again, we can give this a nice name. We call it tau, but this time we give it 4 indices, Nm, they come from the left-hand side, and Kl, they come from this sum and the initial density. And we have to, again, apply a damping factor of mu on each reflection in order to allow us to calculate this infinite sum. Once we have this damping factor here, we can actually rewrite this infinite sum as the inverse of this operator here. And this is one of the two reasons why we are using densities instead of single rays. So the first reason for using densities is that it helps you getting rid of the question of how many rays to actually start. Classical ray tracing problems have the problem that you have to decide how many rays do you start into the domain and when do you consider your result to have converged. If you start densities of rays, well, you always start infinitely many. So in a sense, you solve that problem. But the more important part, I would say, is that by using densities of functions and introducing this density operator here, it gives you a mathematical tool at hand where you can write down an operator equation like that, where you can use this operator and then symbolically write down this inverse here to give you the answer you want from an initial density you have. And to do this numerically, you have to cut off your basis somewhere. So now we changed from a calligraphic T to an upright T to indicate that we are now talking about a finite size matrix. You have to cut it off at some order K. So this order will be denoted in yellowish letters throughout the talk. Having said that, here's a plot of how this matrix would look like. So this is just a visual representation of these two Kronecker deltas. In order to get this 4-indexed monster down to a 2-dimensional plot, you have to somehow fold 2 indices into 1. So if you choose NP to be the number of basis functions available to your second degree of freedom, to psi in that case, you can write down a mapping like that, and then you get a 2-dimensional plot like that. Now, this is how the inverse of 1 minus t would look like. It is still rather sparse, but looks more complicated than what you started with. And this matrix then can be used to calculate this infinite sum down here. Okay, recap. Where did this transfer operator come from? Well, if you have your billiard dynamics, or if you have your ray dynamics through your domain, then you can write down your transfer operator like that. You have to decide on a certain set of basis functions. They go in here, and then you have to integrate this double integral. Just to give you an example, you can use other bases as well. So for example, you could choose a Fourier-Legendre basis, where instead of two Fourier functions like we just did, you could stick with a Fourier function in phi, but you use Legendre polynomials in psi. Why not? You could do that. So you would put them in, and then you have to solve this integral, and it leaves you with this integral here over the product of 2 Legendre polynomials. You could then express those again as a sum of over only one Legendre polynomial, and this is somewhat the Fourier transform of a single Legendre polynomial, and so this could then be written as a certain sum of Bessel functions of half integer order, or you just say, you know what, I'll just do this numerically, that's fine as well. And so the corresponding plot would look like this. So choosing a different set of basis functions gives rise to a different operator T. It gives rise to a different behavior in terms of a convergence with respect to this cutoff. This operator here would yield an inverse operator like that, but all of those would in the end be possible to describe the long-term behavior. Someone has his microphone on. Could I just ask you to maybe mute yourself? Thank you very much. All right, so having said that, what do we have? We have our ray dynamics. We focused on densities, and I introduced this operator for mapping densities through closed domains. I did this for the circle because the overall expression was very simple, but you can do the very same for triangular domains. Now, I already showed you the boundary map for a triangle. At that point, I would like to ask you to just take my word for it that you can do the same and calculate a transfer operator for domains like that. The basis functions we use now are not Fourier functions along this boundary here, but they are piecewise constant functions. So it could be 1 here and then 0 all the way down, and the next basis function would be 0 here, 1 here, and then 0 all the way down, and so on and so forth. And for the directionality, again, we use Legendre polynomials just like in the previous example. We changed the damping a bit. So instead of damping out parts of the energy on each reflection, we take the length of each traveled ray and weight the transfer operator with a damping which is depending on length in this exponential fashion here. It turns out that this mu prime here can be linked to structural damping, also used in finite element computation. So it's linked to the imaginary part of the Young's modulus. Okay, but apart from that, all ingredients are conceptually the same. We have a boundary map, we have a transfer operator, we have densities of rays, and we start densities on edges. So for example, here we could inject a ray of or a density of rays downwards, called rho naught. Again, this is just a post-processing step. Remember that the actual calculation takes place on the boundary map. Now the first reflection would look like this, and again we would look at sums of that in order to walk towards the equilibrium density, which we get from a continuous driving from this side here. So the third iteration would look like this, and the fourth like this, and so on and so forth, until we end up with infinitely many iterations. Again, if I say infinitely many, I mean by calculating the inverse of this operator, which we were only able to do because we introduced these densities and this operator on these function spaces. This was for one triangle. I already showed you that this boundary map also works for many triangles patched together. So we can do the same here. This time I chose a slightly different initial condition. This is an initial condition of a point source. So let's assume the vibrational excitation is on one of those nodes. Well, then you can calculate the analytical solution of this point source locally and project that onto the adjacent boundaries here. So these boundaries here now carry this rho naught. And if we iterate this forward in time, you will see that this triangle moves towards this and this triangle moves outwards to this and this triangle moves to this and this, and so on and so forth. So this is how the first iteration of the density looks like. The second iteration would be this. So you see that from this triangle, you moved outwards here. Here you got back reflected from the outside domain, and you start moving in again. Here you're still on your way out, and so on and so forth, so that when you finally end up with infinitely many reflections, this is what you get. Please note, you see parts of the fact that the amount of basis function is finite in this spatial plot here. So you see this pattern of dark, bright, here, which basically tells you that there's a finite resolution along this edge in terms of piecewise constant basis functions. So here this number was 4, so we only allowed 4 different basis functions per each side. As it turns out, as soon as you have several mesh cells, you can reduce the amount of piecewise constant functions per edge, because you get your spatial resolution not so much by resolving each edge of each triangle, but by the fact that you're resolving all of space by tiny triangles. Okay, let's have a look at this T operator once again. For this example here, this is how it looks like. It's much larger than it was for the circle case, that's for sure. It's much more complicated than for the circular case. It can be calculated as before, so the conceptual steps are not much more difficult than for the circle, but it does look a bit more complicated, but it is very sparse. And Jonathan also mentioned this sparsity already, and he was completely right, because a ray which moves from this triangle to this triangle means that there's the density can only be mapped from this triangle to this triangle. There is no direct connection from this triangle to, say, this or this. And that means that the corresponding matrix, which symbolizes the connections in terms of density transport, is very sparse, because there are only so and so many neighbors you can actually be transported into. Having said that, we could now try our first go at this car example from the very beginning. But there's one more thing we have to talk about beforehand, and that is what happens if the region we are talking about is not flat. Up till now, I only presented transfer operators on flat domains, so it's justified to always talk about rays in terms of straight lines. But as you might know, as soon as you have a bended, as soon as you have a bent object, then rays start to flow on so-called geodesics, and these do not need to be straight lines anymore. Now, how do we take account for that? We consider FEM meshes to be locally flat in each triangle, because that's what the model basically is, but then curvature comes into place where two plates or two shell elements are connected with a finite angle alpha between them. Now, what happens at an angle alpha between two plates? Well, we will see that there's a certain amount of scattering, wave scattering, coming into play, which depends on various quantities. First of all, the material properties, Young's modulus, Poisson ratio, density, thickness of the plates, but also on this angle of alpha. To start with a simple example, let's consider our flat surface again, and let's assume we have a bending wave incident onto this interface between two plates. Let's call this incident angle phi, and if it's flat, it would just propagate throughout the whole domain without any difference. So there, because it's flat, it's just like one big piece of metal, and it just stays a straight line. And this, of course, is independent of the incident angle. So if we choose all incident angles around this dotted line here, what we would get would be a corresponding ray on the other side as well, of uniform length, independent of the angle of psi. Now, this changes if there is an angle of alpha between the plates. First of all, there will be a transmitted wave as before, but there will also be a reflected wave from the interface. So you have a bending wave going in, and a bending wave, parts of the bending wave being transmitted and parts of the bending wave being reflected. Now, it turns out that the external driving frequency of your problem, which is an input parameter to the calculation, yields a certain value of wave number KB. It also yields one for the shear waves, which is considerably smaller. That's just how it works. They just are always smaller than the one for bending waves. But that means if your angle psi gets smaller and smaller and your incident gets closer to being perpendicular, your tangential component gets smaller and smaller. At some point, you are able to excite shear waves as transmitting and reflecting waves as well. And if you get closer and closer to perpendicular incident waves, you will also be able to convert bending energy into pressure modes on the transmitting and the reflecting side. Now again, we can move our incident vector around the whole dotted domain and draw out what the amplitude of each of these reflected waves are. And this is the pattern we get. So you see the predominant amount is still in bending, but there is a considerable amount of pressure and shear as well. You can do the same for the reflection wave. Now this gives a very complicated pattern, so let me take away the arrows. And this is what a representation of the scattering matrix could look like. It depends on which two plates you are joining, I and J. It depends on what modes you are talking. So we were talking in mode was bending, and then you could ask out mode being transmitted or reflected, bending, pressure or shear. You'll get kind of interesting pictures, and these on top of that now also depend on alpha. So if you make alpha, for example, steeper and steeper and steeper, you see how this scattering matrix changes. So this would be the right angle case. Now I have to say, none of that is something we came up with, maybe apart from the stupid Batman joke. This is all based on a work by Langley and Heron from the 1990s. And here's a somewhat different representation of what I've shown up here. So this is the incident angle, and you can see that, so this is for a specific angle alpha here. And for example, if you are incident with a bending wave on plate 1, then the solid color represents transmission. The dashed up here is reflection, reflection into bending, reflection into pressure, reflection into shear. This would be transmission into shear, transmission into bending, transmission into pressure and transmission into shear. And now you can move your incident angle around, and depending on your angle, you get different behavior. Okay, you just have to incorporate that somehow into your T operator. And this then controls global transmission and reflection behavior. So now we've got everything together, all we need. We had our boundary map, we talked about densities, we talked about how to get the T operator, and we talked about how to incorporate curved behavior. So here it is, our car model in all its beauty. Again, this is courtesy from FFT Belgium. This is a calculation done using DEA. The initial excitation was put on one of these shock, so here would be a shock underneath, this would be a shock tower, and we set the initial excitation here. Just to give you a few numbers, the FEM mesh was valid up to 800 Hertz. This is no constraint for DEA, so we could do a calculation for 8,000 Hertz or, oh sorry, that's a typo, it should say Hertz, this mega is wrong. We could do the DEA, but we could do the DEA calculation for 800 megahertz. It would probably not be of any interest to anyone because that's way too high, but the method itself would work, and it wouldn't take much longer to calculate because the method itself does not scale with the external driving frequency. The mesh consisted of 33,000 quad elements, 1,500 tria elements, and we choose this rather coarse basis size. So this is the number of piecewise constant functions per edge of each triangle or quadrilateral, and this is the number of Legendre polynomials. So there's constant, first order, second order, and cubic, and that then leads to a T matrix of size 2.5 million by 2.5 million, so rather big, but it is very sparse. As you can see, there are only 100 million non-zero elements. And an overall calculation like that takes approximately an hour. Most of the time actually goes into calculating these scattering matrices. So the bit of information I just showed you on the previous slides, because you have to integrate them out while calculating your transfer operator. Very important point, and I saw Bruno joining just this morning. So it is very important that you use a preconditioner for solving this problem. This easily reduces your calculation time from the order of hours to maybe a quarter of an hour. So this is something which I cannot press enough. All right, so this with our numerical example, or our industry grade example. But how could we check on the convergence of the DEA method for this example? Well, one way would be to play around with one of the parameters, for example, the number of Legendre polynomials we allow this method to have. But how would we compare this to say a finite element calculation? Well, we choose this red path shown here manually. We just went through it and said, oh, I want to have this path along the structure here, and compare it with an FEM calculation. So this was done by a colleague of mine, Nurkanat Aymakov. He calculated the FEM data for this structure, and now we can plot this FEM data along this red path together with DEA calculations. And let me do this on the next slide. So here again, on the right-hand side, our car part, and here the FEM data along this one-dimensional line, calculated for 800 Hertz, so where the mesh was still valid, and a specific value of the structural damping. Now, if we choose the amounts of basis functions in the directionality basis very small, or smallest, namely 1, this yields to a highly underestimating the amount of vibration reaching the other side of the structure. And the reason for that is that if you only allow for one Legendre polynomial, that is the constant polynomial, you get something which Alain referred to as a Lambertian reflection. So everything which hits any of these edges is reflected diffusively. So you get a diffusive diffusion-like behavior across the whole structure. Now, if you include two functions, you get more directionality and you get a better agreement across the structure. If you go to 4, you are already in good agreement. It looks like the FEM data, but averaged out. This is something you would expect because DEA is in a sense also acting as an averaging behavior. Now, if you go up to 10, you don't see much more change, which we take as a hint on that this model can be solved with only 4 basis functions in Legendre space. Okay, this is one calculation. Here's another one for 2000. I know the model wasn't quite fit for that, but we just wanted to see what happens. Again, the DEA calculation could go to any frequency higher up. This is usually a bit of a problem when you try to compare to numerical data. If you use FEM calculations, then they are bound from the top by the validity of the mesh, but DEA might be shining at very high frequencies because that's where the methods is supposed to be used for. So we usually prefer ships. Ships have the advantage that they are very big, so high frequency there means something like 15 Hertz. So this is usually a bit easier to calculate. Okay, I want to wrap up. I introduced you a few concepts in order to describe what DEA is. So I showed you this boundary map and gave you a small example of how it works. Then we went into calculating the T operator in order to map not only single trajectories but whole densities of rays. We went on to see how this works out for a circular domain. I have not spoken about this. This is work done together with colleagues from Queen Mary University of London, Julia Slepanchuk, Oskar Bandlow and Wolfram Just, where you can actually write down precise error bounds for this T operator for this circular domain. But we focused more on, okay, how can you take all this and put it onto meshes? We talked about what you have to do in order to account for non-zero angles between plates. And then we saw that we can actually calculate the equilibrium density of vibrational excitation for real-world problems like this. And with that, I would like to thank you for your attention.